Well, here we are. We are back talking about push and pop operations in a microcontroller. And so the issue is in these architectures, push and pop are just vitally important. And what we've arrived at is the notion that pushing and popping in RISC-V doesn't have dedicated push-pop instructions. So it turns out that a push and a pop, they're actually two operations each. Essentially, one is to actually to manipulate the data, and the other instruction is manipulate the stack pointer. And so these are the operations right here, examples of push and pop. Now it turns out there's two ways to do this, either way, and it doesn't really matter which way you pick, but I would stick to one, either the green ones or or the black ones here. Okay, so means I'm storing something the on the stack, which means I'm writing something to memory, which means I'm storing something in memory. So there's going to be a store instruction. There it is. I'm storing a register, so it's going to be a store write. So the two things I need to do are first I need to adjust the stack pointer backwards. So the stack pointer is pointing to the top of the stack, which is valid data. It's the most recent thing I put on the stack. I don't want to overwrite that, so the first thing I do is move that stack pointer backwards. I move it back by 4, so that's 4 bytes. And after I execute this instruction, the stack pointer is pointing at a blank piece of data. So at that point, I can actually do my store word. So the store word here is going to take what's in X8 and store it at this address here, and it's going to take the address of the stack pointer plus 0, which is essentially the address of the stack pointer. So this is a push operation, one way to do it. The other way to do it here is simply, it's opposite of this other version here. I can actually store X8 at 4 less than the stack pointer, and then I can come adjust the stack pointer. Okay, so once again, these are equivalent. I just like this one better. Now the pop operation is going to be a load word. I'm going to take something from memory and I'm going to put it into a register. So this is why you see a load word there. And so what I'm going to do here is I like the green one better. Okay, so what I'm going to do is the stack pointer is pointing at valid data at the top of the stack. So that's where I'm going to go first. I'm going to take it from the top of the stack and put it into a register, which is fine. And then I'm going to follow that up with advancing the stack pointer forward. Now this is undoing this, which you can see this is, I'm adjusting the stack pointer by 4 here and adjusting it by -4 there. Not coincidental. I'm always going to keep these the same, we'll say, or not the same, but equivalent. One is advancing the stack pointer in one direction. The pop is advancing the stack pointer in the other direction. So the pushes are going towards lower memory. The pops are going towards greater memory here. And so, yep, this is the better way to do it, but this also works also. So I can actually adjust the stack pointer first and then reach backwards to get the data. Either of these works, like I say. I think you should use the green ones. That's what I always use. So this is a subroutine. I think this was a something we did before that was kind of no, it isn't something we did before. This is actually sort of new. And what I did is I grabbed an old subroutine, and what I'm saying in the subroutine is that this has a nested call. Because this has a nested call, I have to protect the return address. So right when I enter this subroutine, this is a subroutine here, the first thing I do right here is I push that return address onto the stack. Okay, so here's my push operation right here. That preserves the return address value, because when I execute this call right here, it is going to overwrite that return address. So this protects it. If I'm doing a nest, if my subroutine is doing a nested call, I always have to protect that value. And of course, before I return from this subroutine, I've got to restore that return address. So this represents the restoration of the return address associated with this subroutine. If I don't do this, it won't work. So for nested subroutine calls, this is like vitally important. Nested subroutine calls, I'm saving the return address on the stack before I make the nested call, and then I'm popping it off the stack right here before I return. So these are just classic push and pop operations. Okay, so the next thing we need to do here is the notion of bulletproofing these subroutines, and there's just like an art to writing subroutines. Like I say, you only get one set of registers in this RISC-V, and it's shared by all the subroutines and all that stuff. The issue is it's really kind of complicated to always use the same set of registers, and making sure your calling code is or your subroutine calls don't step on those registers. So the way to write bulletproof subroutines is to push. When you get into the subroutine, you push all the registers that subroutine is using. You push them on the stack. I call that essentially saving context. And before you exit that subroutine, you pop all those registers that you're using in that subroutine off the stack. And that way, the calling code does not need to worry about the subroutine stepping on registers, because the registers that are actually used in the subroutine to do any calculation is actually preserved. Now, this makes your subroutines very easy to use by reuse and all that stuff by the calling code. So this is what you always want to do. It's just seriously, when I'm writing subroutine, it's the last thing I do is to go, protect the registers. And the idea is I don't know what registers I'm going to use until I write subroutines. And so, well, you'll see it when I write code. I usually don't protect the registers because it's just actually too much trouble, but it eats up code space and takes time. It's really straightforward. Once you do it a couple times, you get used to it. So let's look at an example here. So this is an example we used before, and the idea here is, write a subroutine that goes to memory and averages a bunch of 32, takes an average of 32 memory locations. Not a big deal. What it was is we put it in a loop, add it up, shift it right by 5 times, and that was our solution. And I think this is our solution right here. Now the problem is, if I execute this subroutine and we'll say the calling code is using register X15 before it made the call, this is going to overwrite this instruction here is going to overwrite X15, and you've lost that data. It's messed up. You have to be really careful when I call the subroutine, because it does change the data in some registers. So essentially it changes the data in, let's see, well, X20, I think that's the answer. It's expected bit. It also changes the data in X10, X15, and X11. So it changes the data in 3 different registers. So the idea to make this subroutine bulletproof is, when I get into the subroutine, what I'm going to do here is I'm going to save the operating context. And I like saying it like that is because this register uses those, and this subroutine uses those 3 registers, and so I want to be able to call the subroutine and not worry about the subroutine, what registers the subroutine uses, because it protects the registers it's using, and it protects them by pushing them onto the stack at the start of the program and popping them off the stack at the end of the program, at the end of the subroutine. Okay, so this is called saving context and restoring context, or at least that's what I call it. And so the idea here is I'm using these 3 registers, X15, X10, and X11, so I'm pushing them right here. Okay, and then when I'm done, I'm popping them off the stack right there. So it doesn't matter what the code in here does, it doesn't tweak those 3 registers. I don't need to worry about it. This makes this using this subroutine, if we were actually to use it, makes it very easy, and I'm always going to do that. Not always. Essentially, if I'm writing real code, I always do it. Oftentimes when I'm just doing code for a lecture or something, I don't put it in there because it's too much trouble. Or particularly examples. The examples, I mean, if you look at this, half this code, big portion of this code space is saving and restoring contacts. It takes time and effort, but it makes your subroutines bulletproof. So let's look at this. So this is actually right here a clunky way to do it. A cleaner way to do it is with this. I can do it in less instructions right here. Essentially, instead of adjusting the stack pointer 3 times, I only adjust it once, and you can see it right here. I know I need to save 3 registers, so I back it up by 12, and then I save it 4 at 0, which is the top of the stack, 4 and 8. So that gives me these 3 stores here. It fills up that 12 bytes here. Remember, I'm working backwards on this. So to restore it, it's the same thing. I'm just doing it all in one operation. Now to compare these things, looks like this. Much nicer code. Essentially, the difference between this code is this is a little bit longer than this. Same exact functionally equivalent code. You know, convince yourself this is the exact same code. This is just the restoration, or the context saving part. It's not the restoration part. So in writing subroutines, I don't often do it. I'm just not going to do it when I'm going over these and recording them. But the optimal way, actually do it in most of the examples in the book. You're writing a subroutine. You give it a header. And so the header is going to say a couple things, is the description of the subroutine, the arguments, that's the values you're sending it, and the values it's returning. Typically speaking, you also want to list, the return values are the registers that it tweaks. Okay, so I always list which registers the subroutine's tweaking, even though oftentimes I make sure it doesn't tweak any registers. So essentially the initialization code in every subroutine, I always write a init when I start it out. You've seen that many times before. Essentially, one of the things I'm going to do if the subroutine has a subroutine call in it, it's a nested subroutine, I'm going to save the return address by pushing it onto the stack. Also, I'm going to make this thing bulletproof by pushing all the registers that the subroutine uses onto the stack. And so this is pretty much context savings. And then what I'm going to do here, typically I have to initialize some working values such as loop counts and stuff like that, or accumulator values. I have to clear accumulators. So the body of the subroutine is going to determine which registers I need to save. And I typically, like I say, I always write the body first, then go back and write the context saving and restoration. So once again, essentially this return preparation is pretty much the undoing of these 2 values right here. If it's a nested subroutine call, I have to restore it, and restore the return address, and I have to restore the registers that it uses. And then I return. So once again, all my subroutines, generally speaking, they have nice headers in them, very informative. That's an initialization code that includes saving the context. As the body of the loop, I restore context, and then I return. So in summary, nested subroutine calls are essentially subroutines that call other subroutines. We run into that a little bit. But another issue here is recursion. Recursion is a subroutine that calls itself. I pretty much try to avoid that at all costs. It takes a very astute person, and it's very confusing, hard to do right. Anyway, we're not going to go into that in this class. I actually do have an example problem where I'll do that, just to show you how interesting it is. One thing you've got to keep in mind here is these call and return pairs involve the stack. If you add the call and return tweak the stack, you have to maintain the call and return orders. So call and returns come in pairs. I mean, I can't do 2 calls and only do 1 return. Generally, I'm going to do 2 calls and 2 returns. The push and pops, the orders are also very important. You know, if you push 3 things, you got to pop 3 things, etc., etc. You have problems with the stack underflow and overflow. This stack is implemented in memory. If you mess the stack up, like don't keep your call and return push and pop pairs in pairs, what's going to happen is you're going to run the risk of overwriting important data, and once you do that, your program's not going to work. And so essentially, remember, the stack is just a piece of memory, part of main memory. In summary, we have a stack, which is an abstract data type. We don't have push and pop instructions in RISC-V. It's part of memory, so what we're going to use is the load and store instructions. So subroutines use the stack. Essentially what I'm going to do when I call a subroutine, I'm going to store the return address in a register, but if I do nested calls, I'm going to have to push that return address, which is an X1, onto the stack. So oftentimes in subroutines, I'm going to save context so I can make their subroutines very usable. I'm going to push all the registers that the subroutine uses onto the stack before I do anything, and then before I exit the return from the subroutine, I'm going to pop all those registers off the stack. That means the calling program doesn't have to worry about which registers the subroutine's using. And typically I always do that essentially when I'm writing real code to make my subroutines bulletproof. And that's it, folks, for that. We will call it done.